Right, okay, today we're going to be looking at using Laplace transforms to solve second order differential equations using the Dirac delta function. So this is example 1. So example 1 says solve d squared y by dx squared plus 4y equals this Dirac delta function t take away 3. And you're given your two initial conditions. When x equals 0, y equals 1. And when x equals 0, the derivative of y is 0. Right, so I've already started this question off. So you know, if you do the Laplace transform of this, we get this thing here. Now I don't have a dy by dx term, so I don't have any term in here. And then if I Laplace transform 4y, I get 4ly. Now if I Laplace transform the Dirac delta function, if you go to your formula sheet for Dirac delta, for Laplace transforms, and you look at this one here, this is your one for Dirac delta functions. So that's 3 in mine, so I'm just going to put 3 up there. So it's going to be e to the power of negative 3s. Right, then as usual I just multiply out my brackets, so I've just multiplied out this bracket and put it all together. So s squared ly take away s plus 4ly equals e to the power of negative 3s. Okay, I've then collected my ly terms together as I always do. So I've got s squared plus 4, and then I've got this rogue negative s or take away s that's sitting in here. That needs to be taken over to the other side because it's not involved in an ly. So that's what I've done in the next line. I've just taken that s over to the other side and it becomes a plus. Right, so I want ly, remember, so I've just divided through by s squared plus 4. Right, now then I looked at my function, right, this thing here, I can't factorise the bottom, I can't complete the square in the bottom, so the only thing I could try, which I think which could help me, is splitting the top, because you can always split the top of a function. So there we go, so split the top of a function here, and that's where I've got to. The reason it's all written out is that I managed to knock over the camera earlier on, so I thought I would redo it. Right, so this here has got an exponential in it. As soon as you've got an exponential in it, you know you've got to use, or an exponential in the top line involving an s. You know you've got to use that second shift theorem. Right. And this one here is just we're just going to see if we can do a normal inverse transform. Okay. So let's just call this bit 1 and this bit 2. Let's just transform them separately and see what happens, right? Okay. So, part 1, I want to do the inverse Laplace transform of e to the negative 3s over s squared plus 4. I think that's the dream. Now, what I could do is I want to get rid of that exponential, because I know that exponential is a horrible thing and it's to do with a second shift, right? So if I rewrite that as e to the power of negative 3s multiplied by 1 over s squared plus 4. That tells me that just like the stuff we were doing last time on Dirac delta functions, that tells me that a is equal to 3. Okay? So that means that all I need to do is find the inverse Laplace transform of my wee s squared plus 4. Now, s squared plus 4 is just 1 over s squared plus 2 squared. Like which, if I look at my inverse Laplace transform table, something with s squared plus a number squared is either sin or it's cos. Now I don't have an s on the top, so that means it's got to be sin. So that means that these two numbers here have to be the same. So that means I need to have 2 or s squared plus 2 squared. Which means I need to, in order to make that work, take out a half here. Because a half multiplied by 2 gives me the thing I started with above. Which is just 1/2 sine. Right, now remember, because I've identified that a is 3 up here, this is happening as t goes to t take away 3 because of the second shift theorem, because this is where these two bits are linked. So this bit here comes down into here. Okay, so and this part only happens when t is greater than or equal to 3. So up until 3 seconds, or if your time's measured in seconds, this wouldn't be involved. But as soon as it hits 3, this would then be added into the function that we're dealing with, or the solution that we've got. Right, let's look at number 2, the second part. The second part was I wanted to find the inverse Laplace transform of this bit here. So again, it's fairly straightforward. That's just s over s squared plus 2 squared, which is just cos 2t. Right now, this happens everywhere. There's no second shift theorem here. Right. So sorry, I'll just note that up. So this bit here has the second shift theorem, so we know that that's affected by the time, right? And we worked out the time at which this impulse or occurrence happens is 3. So this bit in part 1 only happens when t is greater than or equal to 3. Right? Now, part 2 is the normal inverse transform. So it happens everywhere. There's no exponential, so there's no issue to do with t or issue to do with time. So when I find the inverse transform of that, it's cos 2t. Right, so now I need to write my answer. So y equals cos 2t everywhere. So that's when t is less than 3. Right, so when t is less than 3, and it also happens when t is greater than or equal to 3. So cos 2t happens everywhere. Okay? But this 1/2 sine 2t happens when t is greater than or equal to 3. And remember, we need to substitute this in for t. So that's plus 1/2 sine 2t take away 3. And that's my solution to that differential equation. So there's quite a lot of different processes and techniques going in there, and that is fairly complicated. It's got a lot of different things in it, but it's actually quite a short solution. in the grand scheme of Laplace transform questions. Right, here we go. Let's look at a proper one. So we're going to look at a differential equation that's got a Dirac function in it and has got all the partial fraction stuff in it as well. So we're doing a whole lot of different things here. So this is example number 2. Again, apologies for the quality of this pen. It's the best I can do, all my good pens have ran out. Okay, so that means we're going to Laplace transform. I'm just going to write this bit of working down. I didn't in the last question, but I'm just going to just remind you. So you're going to Laplace transform everything. And just like normal, that 2 moves outside the Laplace transform rather than inside the Laplace transform. Right, so this becomes s squared ly, well, take away 0s, let's take away 0, take away 6, plus 6 s ly, take away 0, plus 8 ly equals, I'm a Laplace transform table, so it's a Dirac delta function, so that's one here, and our number is 7. So that's going to be e to the power of negative 7s. Like that, and the 2 is obviously just staying there. Right, so s squared ly equals 6 plus 6s ly plus 8 ly equals 2e to the power of negative 7s. As usual, you're just going to take out your ly as a common factor, s squared plus 6s plus 8. And luckily, I've only got that wee 6. I'm not getting s or anything, so hopefully that's going to make it easier. Right, now remember to check that the thing in that bracket looks the same as the differential equation you've started with. Because if they're the same, then normally you've done everything right. Just a wee kind of check. So ly s squared plus 6s plus 8 equals 2e to the power of negative 7s plus 6. So then ly is equal to 2e to the negative 7s plus 6 all over s squared plus 6s plus 8. Now, if you know that there's been a Dirac delta function involved, it's always easier to split the top of your fraction. You could factorise and continue, but it makes it so much more difficult. So if you've got an exponential on the top, split it up into 2 fractions. So if there's been a Dirac delta function, always split this bit in 2 and do the partial fractions as 2 separate questions, because otherwise it ends up being an absolute mess trying to do it. So think about it like this. This has got your exponential in it, so you know that's going to be second shift theorem. Right, now I can factorise the bottom, but because that exponential takes priority, I split the fraction. Right, I'm going to factorise it later on anyway, and this is just going to be normal inverse transforms. Right, so again I'm just going to call that the bit with our exponential in it, part 1, normal 1, part 2. Right, so what I want to do is I want to find the inverse Laplace transform of 2e to the power of negative 7s over s squared plus 6s plus 8. Right, what we want to do. Right, so I need to get rid of that exponential thing because it's been a pain. So same process as we did before. So it's 2e to the power of negative 7s times 2 over a squared plus 6s plus 8. So I'm just taking out the exponential. That's what you do. If there's something else involved in the exponential, you don't take that out. So that means a equals 7. So something happens at that time 7. Okay. So that just means we're going to try and find the inverse Laplace transform of this thing here. Right, so we know we try and factorise the bottom. Yeah, I can. Adding to make 6. Multiplying to make 8. So it's s plus 2, s plus 4. Which equals a for s plus 2 plus b for s plus 4. So we just complete partial fractions as normal. So substituting your numbers, you've got negative 4 plus 2, so that tells me that b equals negative 1. And then when s equals negative 4, when s equals negative 2, what am I talking about? Sorry, when s equals negative 4 now, when s equals negative 2 now, you've got 2 equals a negative 2 plus 4 plus 0. So 2 equals 2a, so then a equals 1. So I'm now looking to find the inverse Laplace transform of my, whatever this is. So my partial fractions is 1 over s plus 2, take away 1 over s plus 4. There. Now remember, that is happening after t equals 7, because remember a is equal to 7 here, right? So the inverse Laplace transform of that thing there is e to the power of negative 2t. The inverse Laplace transform of that is e to the power of negative 4t. But remember, that's happening as t becomes t take away 7, because remember a is equal to 7 here. Okay, so that's part 1 complete. So remember, this only happens at and after t equals 7, right? Okay, part 2, I need to find the inverse Laplace transform of 6 a squared plus 6s plus 8. Again, it's the same denominator, so I'm just going to factorise that like normal. like that. So it's just the same partial fraction but with a different number on the top. So effectively all it's done is turned it into two partial fractions questions from one partial fractions question. That's all the Dirac delta function is basically doing in terms of difficulty of the question. Right. So 6 equals a s plus 4 plus b s plus 2. Same thing again. S equals negative 4. 6 equals 0. So b is negative 3. And when s equals negative 2, 6 equals 2a. So a is 3. So quite self-explanatory. I don't need to show any more working in that. So normal partial fractions. So now that means I just need to find the inverse Laplace transform. So I've got my partial fractions. A is 3, b is negative 3. I have 3 over s plus 2, subtract 3 over s plus 4, which is 3e to the power of negative 2t, take away 3e to the power of negative 4t from a Laplace transform table. And remember, these happen everywhere. There's not been a second shift in this part of the function, so these happen everywhere. So let's write out an answer. So there's been a second shift theorem, so we know y equals, it's two parts. So something happens at 7. Okay? Now before 7, I've got this function here. 3e to the power of negative 2t, take away 3e to the power of negative 4t. So that happens in both those bits. That happens everywhere. But I've also got this function here, which I worked out in part 1. E to the power of negative 2t, take away e to the power of negative 4t, and that happens at and after t equals 7, so that's in here. So that's plus, and remember, you swap t for t equals 7. E to the negative 2 times t take away 7, take away e to the negative 4 times t take away 7, like that. And I've just put that in a bracket because it's two parts of that function. So you're just adding it in. And if you wanted to, you could simplify that down. 3e negative 2t, take away 3e to the power of negative 4t, when t is less than 7, and 3e to the negative 2t, take away 3e to the negative 4t, plus negative e to the power of negative 2t plus 14, take away e to the power of negative 4t plus 28, if you wanted to really simplify it as much as possible. And that is how you solve second order differential equations using that involve Dirac delta functions. If you look in your workbook at page number worksheet 7. Now, if you look at worksheet 6, where 51, page 51, question 1 and 2. Okay, so if you can have a go at those questions, if you get stuck at any of the answers, let me know. I personally, if you look at question 2, I would multiply everything through by 2 at the start to make it easier. But hey, that's just me. Right now, Aidan asked me a question. It was question 3 on worksheet 5, and it was finding the inverse transform of this function here. We broke it down to this. Now the answer in the back of the book is wrong. I think me and Aidan both got to that stage that we worked out it was wrong. Now, the answer you should have got is similar to the differential equation ones. You should have got that it was 0 everywhere below t equals 1, and then it was e to the power of negative t take away 1 cos root 2 t take away 1 take away 1 over root 2 sin root 2 t take away 1 is what you should have got as the answer to that question. The workings clear quickly for anyone who's tried that question and wants to know how I got to that answer. Right, I will do another lecture tomorrow, and that will be the first one on eigenvalues and eigenvectors. I'm just going to do the absolute bare minimum. I'm going to show you the stuff you need to know, same with double integration, and then that'll be the course over and you can just focus on revision. Okay, enjoy the rest of your day.